The paper delves into the connection between combinatorics and algebraic groups, focusing on the symplectic Grassmannian SPG 2n and its invariant subvarieties. It characterizes these subvarieties using symplectic Coxeter matroids, which are pivotal in understanding the geometry of flag varieties. The study begins by discussing the significance of matroids in understanding invariant subvarieties, as demonstrated in the work of Gelfand, Goreski, McPherson, and Serganova. The authors then utilize the moment map to establish a connection between Coxeter matroids and the geometry of flag varieties, as stated in Theorem 1.1. This theorem is fundamental in characterizing invariant subvarieties of the symplectic Grassmannian SPG 2n. The author's findings contribute to a deeper understanding of the relationship between combinatorics, algebraic groups, and geometry, particularly in the context of symplectic Grassmannians and Coxeter matroids. The symplectic Grassmannian SPG 2n is a homogeneous space for the symplectic group SP2n and a maximal parabolic subgroup P. It consists of two-dimensional isotropic spaces in a 2n-dimensional vector space with a symplectic form. The maximal torus T, comprising diagonal matrices with non-zero entries, acts on SPG 2n, and its associated Weyl group is the hyperoctahedral group BCN. This research characterizes invariant varieties of SPG 2n, using a moduli of irreducible quotients associated with type A and type BC Coxeter matroids. This is achieved by applying the theory of type A matroids of rank 2. Representable over an algebraically closed field of characteristic 0. Notably, each thin Schubert cell in SPG 2n has a unique lifting to a thin Schubert cell in the type A Grassmannian G 2n. The authors establish an explicit description of SPG 2n as a hyperplane section of G 2n using the moment map, revealing the connection between these spaces. This work contributes significantly to our understanding of symplectic Grassmannians and their relationship with type A Grassmannians, offering insights into the structure and properties of these spaces through the lens of Coxeter matroids and their representations. The symplectic Grassmannian SPG 2n is a central object of study in this paper, which explores its connection to rank 2 symplectic matroids. The authors first detail the structure of SPG 2n as a T-variety, where T is an n-dimensional torus. They calculate the T-fixed points, orbits, and stabilizers, providing the symplectic analog of the torus bundle in theorems 3.12 and proposition 3.13. Furthermore, theorem 5.3 describes the invariant subvarieties of SPG 2n. In section 4, the authors obtain a stratification of SPG 2n in theorem 4.8, allowing them to define symplectic analogues of thin Schubert cells and characterize symplectic matroids of rank 2. They also establish a criterion for the representability over C of these matroids. The paper begins by introducing notation and preliminaries, working over the complex numbers C. The projective space Pn is defined with projective coordinates xi, j for I, j, element of 2n, choose 2. Coxeter matroids with respect to the Weyl group W are referred to as W-matroids. The Grassmannian of lines G 2n is recalled, which is the variety of two-dimensional vector subspaces in a complex vector space of dimension 2n. The algebraic 2n-dimensional torus T of invertible diagonal matrices acts on G 2n by scaling the columns of a matrix representation. The Plucker coordinates xi, j, of a point x element of G 2n are used to define the set B x equals I, j, element of 2n. Choose 2. Xi, j does not equal 0. The moment map micro T, G 2n, right pointing arrow R2n is defined, and the polytope micro T, x is used to recover the set B x. In particular, if x equals xi, j satisfies xi, j does not equal 0 for all I, j, element of 2n, choose 2. Then B x equals micro T, G 2n is the hypersimplex increment 2n which is a lattice polytope of maximal dimension 2n1 inside the affine hyperplane H equals x element of R2n. N airy summation I she equals 2. The S2n matroid of x element of G 2n is defined as either the subpolytope micro T x subset of increment 2n or the pair 2n b x denoted by m x. Matroids of rank 2 on 2n are examined with a focus on M2S2n, the set of matroids representable over the complex numbers. Non-intersecting families are introduced as a fundamental concept, and their connection to matroids is established. The quotient set M2S2n S2n is explored, revealing its intimate relationship with partitions. The symmetric group S2n acts on M2S2n, yielding an orbit space isomorphic to the set of partitions π2n. A canonical section π2n right-pointing arrow M2S2n S2n is constructed, allowing for the definition of a loopless matroid M pi for each partition pi. It is demonstrated that M pi is representable, and, in fact, any matroid of rank 2 is representable. The discussion then turns to BCN matroids of rank 2, where the hyperoctahedral group BCN is defined and its connection to admissible sets is elucidated. This framework provides a rich foundation for exploring the properties and structures of matroids of rank 2 on 2n. The concept of symplectic Grassmannians and rank 2 symplectic matroids is introduced, defining a total order on n as admissible if it satisfies certain conditions. A standard admissible ordering is established, and for any admissible order, a partial order on J2n is defined, equivalent to the W-shifted Bruhat orders for BCN. A BCN matroid of rank 2 is defined as a triple M equals n b, satisfying the maximality property, where B has a unique maximal element with respect to every admissible order on n. The set of bases of M is denoted as B, and the action of BCN on M2 BCN is defined. Two BCN matroids are considered isomorphic if there exists tau element of BCN such that tau b equals B. The number of admissible orders on n is 2nn, with half being the opposite orders of the other half. The maximality property is equivalent to the minimality property, and every matroid B subset of J2n less than is contained in an interval a b equals x element of J2n. A is less than or equal to x is less than or equal to b. An example is provided for n equals 2, where there are 2 to the power of 2 equals 8 admissible orders, and the admissible orders on J2n are listed. The set M2BC2 has 15 elements, and the group BC2 is the dihedral group D8, with M2BC2, BC2 having 5 orbits. The symplectic Grassmannian of isotropic lines is a projective variety defined over a complex vector space V of dimension 2n, endowed with a non-degenerate alternating bilinear form omega. Given an integer 1 is less than or equal to k is less than or equal to n, an element W element of G, k, 2n, is isotropic if omega, W equals 0. This variety can be described as a homogeneous space SP2n, P, where P is the stabilizer of an element W element of G, k, 2n, under the action of SP2n. The symplectic Grassmannian is also a linear section of the Grassmannian G, k, 2n. The natural map SPG, k, 2n, asymptotically equal SP2n, P right pointing arrow GL2n, P, asymptotically equal G, k, n, is a closed embedding. The Schubert cells in SPG, k, 2n, are restrictions to SP2n, P of the Schubert cells in GL2n, P. The symplectic Grassmannian, denoted as SPG, k, 2n, is a complex geometric object that has garnered significant attention in recent years due to its intriguing properties and potential applications in various fields of mathematics and physics. This geometric object is defined as the intersection of two distinct spaces, the Grassmannian G, k, 2n, and the projective variety P, Kirk, where the vanishing ideal is generated by Plucker relations and symplectic linear relations. In this context, the embedding of SPG, k, 2n, into P, Kirk, is non-degenerate, meaning it does not collapse or become singular at any point. Moreover, the codimension of SPG, k, 2n, inside G, k, 2n, is k squared, indicating the dimensionality difference between these two spaces. However, the symplectic Grassmannian is a smooth complete intersection only when k equals 2. This specific case, known as the symplectic Grassmannian of isotropic lines, exhibits unique properties that make it particularly interesting for researchers. For instance, the homology groups Hi, SPG, 2, 2n, Z, can be studied in detail, providing insights into the topological structure of this geometric object. An example of such a study involves examining the homology classes of Schubert varieties in G, 2, 2n. These classes are fundamental in understanding the algebraic and geometric properties of the symplectic Grassmannian and its relationship with other geometric objects. The general discussion on these homology classes offers a deeper understanding of the symplectic Grassmannian's role in various mathematical contexts, including representation theory, differential geometry, and algebraic geometry. Overall, the symplectic Grassmannian is a fascinating geometric object whose properties and applications continue to be explored by mathematicians and physicists worldwide. Its unique characteristics, particularly in the case of k equals 2, make it an essential area of study in modern geometry and beyond. The authors define Schubert varieties in the symplectic case, denoted as sp sigma, I, j, which are subsets of the symplectic Grassmannian SPG, 2, 2n. These varieties are characterized by the condition that the Plucker coordinates, k, l, are not less than or equal to I, j, in the poset, j2n, is less than or equal to. The authors prove that the homology classes of these varieties generate the homology ring H** operator, SPG, 2, 2n, z. The dimension of the Schubert varieties is given by proposition 3.4, which states that dim C, sp sigma, I, j, is equal to p, I, plus p, j, 3 if p, I, plus p, j, less than 2n plus 1, and p, I, plus p, j, 4 otherwise. The symplectic Grassmannian is also discussed as a T variety, where T is a maximal n-dimensional torus in sp2n. The action of T on the symplectic Grassmannian is defined explicitly in terms of Plucker coordinates, and the T-fixed points are shown to have a specific form. Additionally, the authors introduce the notion of B, X, which is the set of I, J, in E underscore N, squared such that the Plucker coordinate X underscore I, J is non-zero and I, J, is in Jn squared. This concept is analogous to B, X, in the classical case. The concept of symplectic Grassmannians and rank 2 symplectic matroids is explored, focusing on the BCN matroid structure. The moment map micro T for a toric variety Tx of dimension 0 is less than or equal to D is less than or equal to N is defined, satisfying equation 3.10, and related to the Coxeter matroid of rank 2 on N, tied to the hyperoctahedral group BCN. The polytope SP increment 2, 2n, is introduced as a lattice polytope of maximal dimension n, representing the BCN matroid of a generic point X in SPG, 2, 2n. For the case n equals 2, an example illustrates the set SP increment, 2, 4, as a square with 4 T-fixed points and 15 possible BCN matroids, summarized in a table. The concept of M2 BCN, C, is defined as the set of BCN matroids of rank 2 on N representable over C, noting that not all BCN matroids are representable over C, unlike the SN case. The symplectic thin Schubert cell SPGN associated to a matroid N in M2 BCN, C, is introduced, which is non-empty and corresponds to a specific subset of points in SPG, 2, 2n. In the realm of matroid theory and algebraic geometry, a crucial relationship exists between matroids, Schubert cells, and torus actions. A key result, as stated in Lemma 3.8, is that if a matroid M is of type A and representable over C, then the stabilizer of any element in the thin Schubert cell GM under the action of the torus T depends solely on M. This lemma provides insight into the interplay between matroids and their associated Schubert cells. However, it should be noted that this result may not apply to type BC matroids, with a weaker version available in Lemma 4.12. Furthermore, the relationship between the Schubert cell GM and the hypersurface H, defined by the equation 3.3, is explored in Lemma 3.10. The lemma presents three distinct cases based on the number of pairs, J, in the matroid B in the first case, where no such pairs exist. GM is entirely contained within H in the second case, with only one pair, the intersection of GM and H is empty. Lastly, in the third case, where there are at least two pairs, GM intersects H in an irreducible hypersurface. The paper also delves into the existence and irreducibility of the categorical quotient GM. H equals GM intersection H, TM, as addressed in Lemma 3.11. The authors demonstrate that this quotient exists and is irreducible by leveraging the fact that the torus Tm acts freely on GM intersection H, as established in Lemma 3.8. This finding is pivotal for further analysis and applications in the field of matroid theory and algebraic geometry. The authors demonstrate the irreducibility of the symplectic Grassmannian GM, a crucial component in the study of symplectic matroids. They prove that if GM intersects a subspace H, then the intersection GM intersection H is also irreducible. This is achieved through the construction of a fibration Tm right-pointing arrow, GM intersection H, right-pointing arrow GM, H, where Tm is the tangent bundle of GM, and H is a subspace of GM. The authors then establish theorem 3.12, which states that if GM intersection H is non-empty, there exists a fibration Tm right-pointing arrow, GM intersection H, right-pointing arrow GM, H, satisfying specific dimensionality conditions. The proof involves applying lemmas 3.10 and 3.11 to the fibration Tm right-pointing arrow GM right-pointing arrow GM. Next, the authors prove proposition 3.13, which states that if GM intersection H is non-empty, there exists a surjective map pi GM, H right-pointing arrow GM, whose fiber at X element of GM is T intersection H, Tm. The proof involves defining an action of Tm on T intersection H and showing that the map pi is surjective. The authors also discuss the case when GM subset of H, and show that in this case, T intersection H is isomorphic to Tm, in GM, H is isomorphic to GM times Tm, Tm. They also discuss the case when GM intersection H is a hypersurface, and show that T intersection H is isomorphic to a hypersurface of Tm. Finally, the authors introduce the moment map micro T, G, 2n, right-pointing arrow R2n, which is used to study the Coxeter matroids of type BCN. They show that the image of the moment map is contained in the polytope increment, 2n, which is defined as the convex hull of certain vectors in R2n. Coxeter matroids, specifically S2n Coxeter matroids M, X, and BCN Coxeter matroids M, X, are introduced as lattice subpolytopes of increment 2n, and SP increment 2n, respectively. The moment map micro T for the torus T and its action on SPG 2n is defined, with its image contained in the polytope SP increment 2n. The projection map pi R2n right-pointing arrow Rn is defined, sending A to epsilon I, with its kernel spanned by A plus A. I equals 1, n. The Archimedean tropicalization maps log ring operator are introduced, and a commuting diagram relates the maps log ring operator and pi. Proposition 4.2 establishes a relationship between BCN and S2n matroids, showing that M, X, equals pi, M, X, where M, X, is a BCN matroid and M, X, is an S2n matroid. The proof relies on the linearity of pi and the definitions of M, X, and M, X. Corollary 4.3 states that if increment n is a symplectic matroid representable over C, then pi caret 1 increment n is non-empty. A symmetric matroid M equals E pi is defined as a pair consisting of a set of labels E and a non-intersecting family pi of subsets of E. The degree deg M of a matroid M is defined as the number of indices I such that I element of PA and I element of PB, where A does not equal B. Additionally, two operations of codimension 1 that can be performed on pi are mentioned, as discussed in 6. The concept of symplectic Grassmannians and rank 2 symplectic matroids is discussed, focusing on their properties and transformations. Two operations are introduced: erasing a label, which removes a base containing a specific label, and merging two bags, which combines two bags into one. A combinatorial version of the projection pi is also presented, defined as pi m equals n asterisk operator b pi m, where b pi m equals b m I asterisk operator I element of a m. This projection removes certain bases from the original matroid M to create a new matroid with a different set of bases. A key result, presented in Lemma 4.7, states that if two matroids M1 and M2 have the same symplectic projection, then there exists a matroid M such that pi M equals pi M1 equals pi M2, and the composition of merging some bags results in M1 and M2. This is proven through induction, starting with the case where A, M2, A, M1 contains only one element and then generalizing to the case where it contains multiple elements. The relationship between the octahedral Grassmann-Plucker relations and the bases of a matroid is also discussed, emphasizing how these relations can be used to determine the presence of certain diagonals in a matroid. The research focuses on the relationship between two matroids, M1 and M2, with a specific emphasis on their representability over the complex numbers. It is demonstrated that if both matroids are representable over C, they share a common refinement. This refinement is achieved by identifying certain subsets of the matroid bases and utilizing the octahedral Grassmann-Plucker relations to determine the presence of diagonals. The study also delves into symplectic matroid polytopes, particularly the set pi1, increment n, which comprises all matroids with a given symplectic matroid polytope image under the projection map pi. The paper concludes with a theorem on the irreducibility of symplectic thin Schubert cells, outlining a condition for the existence of a maximal member in pi1, increment n. Symplectic Grassmannians and rank 2 symplectic matroids are explored in this section, with a focus on their decomposition and properties. A decomposition of SPG 2n is introduced as a union of locally closed sets, each defined by an S2n matroid M with degree d, e ratio equal to 1. The authors then prove that a symplectic matroid N of rank 2 is representable over C if and only if there exists an S2n matroid M of degree d, e ratio equal to 1 such that pi m equals n. This result highlights the connection between symplectic matroids and their lifting to symmetric matroids. The concept of an asymmetric lifting of a representable symplectic matroid of rank 2 is defined as a symmetric matroid M that satisfies pi m equals n. An example is provided to illustrate this concept, demonstrating how a given symplectic matroid N can have multiple asymmetric liftings M, resulting in different sets of bases B, M, and B, N. The stabilizer group stab T, N, for a specific symplectic matroid N is also discussed, consisting of diagonal matrices with certain conditions on their entries, ensuring that lambda I equals lambda I and lambda J equals lambda J for all I, J. This result underscores the importance of understanding the stabilizer groups in the context of symplectic matroids and their liftings. This section contributes to the understanding of symplectic Grassmannians and rank 2 symplectic matroids, providing insights into their structure, properties, and relationships with other matroidal objects. The findings presented here are crucial for advancing research in this field, particularly in the context of geometric and combinatorial aspects of matroid theory. This section of the research paper delves into the stabilizers of two matroids, N and M, emphasizing their relationship and properties. Matroid N is assumed to be a BC2N matroid, which admits both a degree 0 lifting M0 to an S22N matroid and a degree R is greater than or equal to 2 lifting Mr to an S22N matroid. The stabilizers of these matroids, denoted as stab T, N, and stab T, M, are examined in detail. The paper begins by defining the stabilizers for N and M, noting that stab T, M, is a subgroup of stab T, n, with an index of at most 2. It then provides a proof for this claim, focusing on the case where A, M, equals J1, Js, and n equals Q1, Qr, with r is greater than or equal to 3, r is greater than or equal to s is greater than or equal to 2, and Ql equals Jl. Jl, for 1 is less than or equal to L is less than or equal to r. The stabilizer of n, stab T, n, is defined as a set of diagonal matrices with entries lambda I and lambda j, where lambda I equals plus or minus 1 and lambda j equals plus or minus 1. Meanwhile, the stabilizer of M, stab T, M, includes additional constraints due to the presence of B, M, equals B, N, union, JL. JL, 1 is less than or equal to L is less than or equal to S. The paper further explains that diag, lambda 1, lambda n, lambda 1, element of stab T, n, if and only if lambda j1 equals lambda j1 equals lambda junior, and diag, lambda 1, lambda n, lambda 1n, lambda 1 element of stab T, n, if and only if lambda j1 equals lambda j1 equals lambda junior equals lambda j1r equals plus or minus 1. A detailed proof is provided for the case when r equals 3, demonstrating that lambda j2 equals lambda j2 equals lambda j3 equals lambda j3 equals lambda j1 equals lambda j1, which implies that lambda j2 equals lambda j2 equals lambda j3 equals lambda j3 equals lambda j1 equals lambda j1. Finally, the paper concludes by highlighting the importance of understanding the relationship between the stabilizers of n and m, as it can reveal insights into the structure and properties of these matroids. The paper explores the connection between symplectic Grassmannians and rank 2 symplectic matroids, proving that the additional conditions for a matrix to belong to stab T, M, are automatically satisfied. This leads to the conclusion that stab T, N, equals stab T, M. To simplify the notation, the paper proves the lemma using equations 4.8 and 4.9, which describe the conditions for a matrix to belong to stab T, N, and stab T, N, respectively. The proof is demonstrated for a specific case, with the general case following the same pattern. A corollary then establishes the dimension of the action of ton on SPGN, showing that the action is closed. This research contributes to the understanding of symplectic geometry and its applications in matroid theory. In the context of representable symplectic matroids of rank 2, normal symmetric liftings play a crucial role. Corollary 4.14 establishes that for any matroid n in BC2n, there exists an irreducible, universal geometric quotient SPGN equals SPGN, T, which may be a non-separated scheme. This result is derived from Sumihiro, 10, and Corollary 4.13. Notably, the notation Tn equals T, stab T, M, is introduced, where M is a symmetric matroid such that B, M, E, adio, / equals, I, for some I in, N. The symplectic projection pi, M, of this matroid is a non-empty set, and if deg, M, E, adio, / equals 1, then pi, M, is a representable symplectic matroid. The paper presents 3 cases for representable symplectic matroids n of rank 2 over n equals, n, union, n. In the first case, n admits only a symmetric lifting of degree d less than 1, resulting in M2S2n down pointing arrow n equals, n. In the second case, n only admits symmetric liftings of degree d greater than 1, and so M2S2n down pointing arrow n equals, max, n, where max, n, is the maximal symmetric matroid projecting to n as in theorem 4.8. Finally, in the third case, n admits both a symmetric lifting of degree d less than 1 and one of degree d greater than 1, resulting in M2S2n down pointing arrow n equals, n, max, n. The set of normal symmetric liftings M2S2n down pointing arrow n provides a novel way to express these objects as symmetric matroids, which could be beneficial for describing the set M2BCN, BC, of equivalence classes of representable BCN matroids of rank 2. However, the behavior of the set M2BCN, M2BCN, BC, of symplectic matroids that are not representable remains unclear. An example is provided, illustrating a symplectic matroid N that does not admit a lifting of degree d, e, adio, / = 1 and is therefore not representable. This raises questions about the nature of non-representable symplectic matroids and whether they can be obtained as the symplectic projection pi m of a symmetric matroid with deg m = 1. The authors delve into the concept of tinvariant schematic points, focusing on the symplectic thin Schubert cell SPGN, which is an irreducible tinvariant space as per theorem 4.8. They calculate the dimension of SPGN using corollary 4.14 and corollary 4.13, which state that the universal geometric quotient SPGN, T exists and is irreducible, and all fibers have the same dimension, respectively. The authors introduce the concept of a matroid M equals E, pi, with length L, m, and weight W, m, and define a symmetric lifting of a representable symplectic matroid N of rank 2. They then present theorem 5.2, which provides a formula for the dimension of SPGN in terms of the weight and length of the matroid M. The formula depends on the degree of M, with three possible cases: L, m, equals 2, L, m, greater than 2 with deg, m, less than 1, and L, m, greater than 2 with deg, m, greater than 1. The proof of theorem 5.2 relies on the decomposition of Gm, the torus bundle decomposition of Gm, and the dimension of the fiber and basis in the torus bundle decomposition. The authors also explain the case where the degree of M is 0, where the thin Schubert cell is contained in the hyperplane. They then define a subvariety Vn, y, of SPGN, given a subvariety y of SPGN, and prove theorem 5.3, which states that a tinvariant subvariety y of SPG, 2n, is of the form Vn, y, for a unique M, y, in M2BCN, C, and a subvariety y of SPGM, y. The proof involves theorem 4.8 and the fact that y is closed and irreducible. Computation of tinvariant subvarieties for the symplectic Grassmannian SPG, 4, is facilitated by theorem 5.3, which enables classification of these subvarieties into 4 categories based on their real dimensions: 0, 2, 4, and 6. A symplectic analog of 6, theorem 3.2, is presented as corollary 5.5, describing the relationship between the functor of points Vm and the cycle map H. This corollary factorizes through the projection given in equation 5.3, connecting the set of isomorphism classes of representable symplectic matroids of rank 2 to the quotient space SPG, M. The computation of tinvariant subvarieties is crucial for understanding the geometric and algebraic properties of the symplectic Grassmannian SPG, 4. By categorizing these subvarieties according to their real dimensions, this research provides new insights into the symplectic geometry of this space. Furthermore, corollary 5.5 establishes a fundamental connection between the functor of points Vm and the cycle map H, which has significant implications for the study of symplectic matroids and their representations. The projection given in equation 5.3 plays a key role in this connection, allowing for a deeper understanding of the relationship between symplectic matroids and the symplectic Grassmannian. The page presents a list of key findings and implications derived from the research conducted on the subject. It highlights the importance of understanding the complex interplay between variables in the system under study, emphasizing the need for further exploration into the mechanisms that govern these interactions. The research reveals significant correlations between certain factors, which are crucial for predictive modeling and policymaking. These correlations suggest that small changes in one variable can have profound effects on others, underscoring the nonlinear nature of the system. Moreover, the study emphasizes the role of feedback loops as critical components in the system's dynamics. These loops, both positive and negative, play a pivotal role in amplifying or dampening the effects of changes within the system. The authors argue that a deeper understanding of these feedback mechanisms is essential for developing effective interventions. The page also touches upon the limitations of current methodologies used in studying the system. It points out that traditional linear models often failed to capture the complexity and nonlinearity inherent in the system, leading to inadequate predictions and policy recommendations. In conclusion, the page underscores the necessity of adopting a more nuanced approach to understanding the system, one that accounts for its inherent complexity and nonlinearity. This involves not only identifying correlations and feedback loops but also developing novel methodologies capable of capturing these dynamics accurately.